Deixa eu ver aqui. Olá, pessoal. Muito boa tarde. Então, sejam todos e todas muito bem-vindos, muito bem-vindos. A gente vai, então, começar a segunda parte do nosso evento, agora no período da tarde. E agora, então, é com muito prazer que nós vamos ter um palestrante, que eu não sei se eu sei pronunciar o nome dele de maneira correta, né? Ops, calma aí. Huang, ok? Depois eu vou fazer a apresentação, só que eu vou fazer a apresentação em inglês aqui, a palestra dele será em inglês, tá? Então, eu espero que vocês estejam gostando do evento. Peço desculpas antecipadamente pelas nossas condições físicas, porque os aparelhos de ar-condicionado não estão funcionando, tá? Então, mas, tirando isso, eu espero que fique tudo bem, ok? Ok. Agora eu vou mudar para o inglês. Hello, everyone. Welcome to our workshop, Quantum Computing. Now it's a pleasure to introduce to you Huang. Huang, also known as Robert, is a visiting scientist at MIT and a research scientist at Google Quantum AI. He received his PhD in 2023 under the guidance of John Prescott and Thomas Wittke. Robert will join Caltech as an assistant professor of theoretical physics next year. His research focuses on quantum information theory, quantum memory physics, and learning theory to advance our understanding of quantum phenomena and accelerate scientific discovery. He aims to develop quantum machines capable of exploring new frontiers in quantum mechanics and beyond. Now, Robert will talk about learning in the quantum universe. So, Robert, thank you again for your acceptance. Have a nice talk.
Thank you so much. Thank you for the introduction. I'm Robert. Today I'll be talking about learning in the quantum universe. This is going to be covering a series of results with my wonderful collaborators, Richard Kuhn, Giacomo Torlai, Victor Albert, John Prescott, Sitan Chen, Jordan Kotler, Jerry Lee, Michael Broughton, Jerry McLean, and many others. As scientists, we know that a central goal of science is to learn how our universe operates from the most microscopic scale, such as the behaviors and the phenomenon arises in atomic systems, molecular systems, to its interaction with photon, to the most macroscopic objects such as planets, stars, black holes, etc. And because our universe is inherently quantum mechanical, the ability to efficiently learn in the quantum universe could lead to many potential advances. For example, if we are able to efficiently predict how a collection of molecules will interact with one another in different scenarios, then it can potentially lead to better catalysts, to better pharmaceutics for curing different illnesses, etc. On the other hand, if we can efficiently extract exotic topological property of a many-body quantum system, it can also help us gain new physical insights into quantum matter that people are excited in exploring in recent years. And finally, with the ability to understand and to learn the inner workings of these highly intricate quantum devices, it can lead to various quantum advantages in sensing, in communication, and in computation. And hence, if we wanted to accelerate and to automate the development of quantum science, it is very important to understand how we can design better algorithms to learn in the quantum universe. And that's essentially the topic that I'm going to cover in today's talk. So before going into the results, I wanted to first clarify what I mean by learning here. So the way I think of learning is it's a much more broader subject than what one might have heard of in, say, training deep learning models for doing question answering, etc. So here we consider learning as the combination of the following 4 information processing steps. First, there's going to be an unknown that we would like to focus on, an unknown aspect of our universe. This unknown could just be the state of a quantum system. It could be the possible dynamics that happen in the quantum systems. It can even be something more abstract. For example, it can be the entire phase diagram. As we tune the different parameters, how does the phases of matter changes? It can also even be the mapping from Hamiltonians to the ground state. How can we learn that unknown mapping? So first, in learning, one will consider receiving information about that unknown aspect by performing experiments, by performing measurements. And then after that, we will process these information that we collected about the unknown to form predictive models. This model can be a theory, it can be a neural network, it can be a tensor network, it can be some other representation most suitable for making predictions. It can be all kinds of different things. We will store these models such that subsequently we can use these models to make accurate predictions in a new setting. So under this definition, a lot of different things are learning. So it can be training a machine learning model to predict the behavior of catalysts or predict protein folding, which won the Nobel Prize recently. It can also be designing a specialized algorithm that try to understand, characterize, and benchmark quantum devices. That's also a form of learning. So in today's talk, I'll be focusing on this more broader definition of learning and try to answer the following question, or try to make some of the initial steps towards answering this broad question of how to efficiently learn in the quantum universe. I will divide my talk into 2 parts. The first part will be focusing on learning in the quantum universe using classical machines, classical computers, and classical strategies. Then the second part of the talk, I will focus on learning using quantum machines. In particular, the sub-questions, the smaller question that we'll be focusing on are the following. In terms of learning with classical machines, we will be focusing on understanding what can classical machines learn about the quantum universe. And furthermore, we're going to look into how classical machine learning models can outperform any non-machine learning algorithms. In particular, this part will be focused solely on learning using classical machines. And later on, we will try to answer the question, which is, can quantum machines learn much faster or predict much more accurately than classical machines? So let me begin with the first part of the talk, on learning using classical machines. In particular, this part of the talk will cover these 3 papers: predicting many properties of a quantum system, power of data, provably efficient ML for quantum problems. Let me begin with the first one, which will set the stage for everything that comes after it. In particular, this paper proposes this formalism called the classical shadow formalism. And this formalism was developed because we were wondering about this very high-level question, which is, in order for classical machines to learn in the quantum world, it has to first be able to see quantum many-body systems. So what do we mean by seeing here? So seeing here, of course, there's different way of formalizing it, but the one that we find most suitable is the following: is that by conducting experiments, the classical machine is able to convert the quantum system, an unknown quantum system, into an efficient or just a general classical representation, such that from that representation, one can accurately predict many properties of the quantum system. And hence, the classical machine can just look at, operate, and manipulate this classical representation as a surrogate for understanding the quantum system. So now, what are some of the traditional methods for doing this? One of the most well-known standard approach for learning quantum system is known as quantum state tomography. Here, one focuses on the canonical representation of an n-qubit state, which is a density matrix representation given by a 2 to the n by 2 to the n PSD matrix with trace 1. In quantum state tomography, the goal is to learn this exponentially large matrix. And because we are trying to learn an exponentially large representation, even the optimal protocol would have all kinds of complexity that grows exponential in system size. The sample complexity, which means how many times you have to do measurements and how many copies of the state do you need, grows as 2 to the 2n. The quantum resource for doing it would also grow exponentially. And because the classical representation is an exponentially large matrix, the classical storage also grows as 2 to the 2n. And finally, because we need to manipulate these huge matrix, the classical post-processing time would also scale exponentially. And hence, as we have started to create a few hundred, or even, say, in Rydberg atom system, a few thousands of qubits, the standard approach really becomes very limited in learning quantum system. More recently, people have proposed different ways of doing it. And given by the promise and given by the power of deep learning models, people have also explored using deep learning for learning quantum states. Here, the idea is pretty simple. We try to perform some simple quantum measurements on the system, and then use those measurement data to try to train a neural network to represent the state. One of the famous protocol for this is the POVM neural network tomography by Huang et al. However, similar to all deep learning-based models, the biggest downside of this approach is that it's essentially a heuristic. While the quantum resource is very simple because it just implements, say, a short depth circuit followed by some measurements, the guarantee that comes out of the deep learning methods is very uncertain. For example, how many measurements do we need in order to really learn the state? It's not known. And this could be exponential in system size still, even though one try to utilize neural network models. And depending on the sample complexity, the memory size to store it might also become unbounded. Say we need to use an exponentially large neural network in order to properly represent the quantum state, for example. And hence, deep learning model, while it has many promises, it's not particularly great for learning quantum state, especially in settings where we wanted to do benchmarking. We wanted to be certain about what is the performance of the quantum device. And sometimes neural network can given it's a heuristic, it can hallucinate, it can produce erroneous claims, produce wrong results, etc. And hence, because of this, what one really wants is to find a provably efficient procedure that can really do the following, kind of following from the promise on the neural network methods. First, in the step 1, we would take all these data by performing, say, simple and not a lot of measurements. And from there, we will try to learn a classical representation of an unknown n-qubit state. Then our hope is that in the second step, we can then utilize this representation to predict a huge number of properties of the quantum state role. So a large number of properties, O1, O2, O3, can come, and we hope that the machine, the classical machine, is able to take in the representation and take in this property, produce the correct estimate for these properties. And that's essentially what we achieve using the classical shadow formalism. So the main theorem that was proved in our work is the following. Let capital M be the number of properties that we would like to predict. Let B be a norm bound, kind of controlling how big are these observables. And finally, epsilon is the error we wanted to be able to predict things. Then we proved that there exists a procedure that can learn a classical representation of any unknown n-qubit state role by performing B log M over epsilon squared measurements, such that after that, given any capital M observables, O1 through OM, with a norm bounded by B, the procedure can use this classical representation to predict the expectation value of all of these different observables up to epsilon error with high probability. Essentially matching the procedure or the kind of the hypothetical procedure that we wanted to have. So for example, if we wanted to predict 10 to the 6th properties, so capital M is 10 to the 6th, all of them has a norm bounded by 1, then naively, if we just go through each properties one by one, then we will need 10 to the 6 over epsilon squared measurements. However, what was quite nice from the theorem is that it shows we only need to take a logarithmic in m, and hence 6 log 10 over epsilon squared measurements instead of 10 to the 6 over epsilon squared measurements. An exponential improvement in the number of properties that we can predict. And furthermore, when we're doing the learning of the quantum state, we don't need to know what these observables are. We're really learning like a effective model of the quantum system, a effective classical model of the quantum system, such that we can predict all of these observables afterwards. And furthermore, this procedure, even though the statement is stated as exists a procedure, we can easily construct such, and the procedure is also very simple. So what is the procedure? Again, the procedure consists of 2 parts, the part on taking data, and then the second part on making predictions. On the data acquisition part, the procedure is just repeating the following few steps for t times, where t is the number of measurements that we would like to perform. So first, we will sample a random Clifford circuit, UI. So Clifford circuits are well known to be classically simulable. To evolve the system, we would then, after evolving it, we would then measure the system in the computational basis, the standard basis, to obtain a bit string BI. And now we just store the classical shadow representation, which is given by this form here. So intuitively, one can think of this procedure as the following. We have this high-dimensional object, which is the quantum system. It's an exponentially high-dimensional object. The random unitary that we apply essentially allows us to look at the high-dimensional object from a random angle, which then projects it onto the classical plane, the classical space. So think of the bit string that come out of it as being the output from it. And now by combining the angle that we're looking at, which is this unitary circuit, followed by the thing that was projected, which is this classical bit string, we can try to reconstruct what this high-dimensional object looks like. For example, if in the first run, we look at it from this angle and we see B1, and then we look at it from a different angle, we see B2, look at it from another angle and we see B3. Now, through all of these different angles and the corresponding projection, or the shadow, on the classical space, we can try to reconstruct what this, or try to get a sense of what this high-dimensional object looks like. And one thing to note is that the classical shadow formalism looks like this. Particularly, the key object is this state, UI dagger BI. And because UI is a random Clifford circuit, UI dagger BI would just be a stabilizer state, which can be represented efficiently on classical computer using order n squared classical bits. And hence this classical shadow, even though formally it looks like it's a quantum state, it can be represented very efficiently on classical computer. So now, given these classical shadows, how can we make predictions? How do we predict properties of the quantum state rho? The algorithm is very simple and it looks like the following. Suppose we wanted to predict the excitation value of an observable O on the quantum state rho. What we would do is we will compute these values xi, or more precisely x1 through xt, where we just replace rho by these classical shadows sigma I hat. Recall that previously the sigma I hat can be represented as a stabilizer state, and one can estimate this quantity to generate a real value. Now what we do is we chunk up all these real values, capital T of them, into K chunks, capital K chunks. For each chunk, we calculate the average. So this is just a standard average. And then after that, we take the median of these K values to produce the prediction O hat. And this is known as a median of mean estimator. And the purpose of doing median of means estimation is because in certain worst case scenario, these xi, if we are very unlucky, it can be a very large number. And if in that rare worst case scenario it happens, then the value can be very bad. Like there could be some number that's super large. So taking the average will be very bad, because average, taking mean, is very sensitive to outliers, and it can completely destroy the estimate. However, median is much more robust, and hence by first performing means and then followed by median, it allows us to predict these quantities much more accurately. And together, using these two procedures, one will be able to establish the theorem before. But let me just provide a very brief sketch of the proof. So the first thing is that the first moment, if we want to look closely, the first moment, which is what is the average of this classical shadow if we average out over all the randomness, it has a very nice closed form solution given like here. And it corresponds to essentially the fourth moment, or if one is familiar with design, then it corresponds to the second unitary design property of random Clifford circuit. On the other hand, the second moment, which corresponds to the variance of this classical shadow, corresponds to the sixth moment of the random Clifford circuit. So here moment just means how many times. The fourth moment means that UI appears 4 times. 2 of them with UI, 2 of them with UI dagger. Now, essentially, one can utilize this very powerful technique known as Weingarten calculus to fully characterize the moments of random exponential size circuit or random Haar-random circuit. These moments correspond to the symmetric group. In particular, it is well known that random Clifford circuit matches these random exponential size circuit up to the 6th moment, even though Clifford circuits are only of quadratic size. Now, by combining Weingarten calculus and the formula for these first and second moment of classical shadow, we will see that when we take the average of classical shadow, it's actually exactly equal to the quantum state that we wanted to learn. So up to random fluctuations, we will know that sigma I hat, the classical shadows, will be approximating the quantum state rho. And now the important bit is when you wanted to control the random fluctuation, then we have to look at second moment. In particular, one can show that the second moment, using Weingarten calculus, is well controlled despite having this exponentially large factor that's lurking in the formula. And because median of means estimator only requires looking at the first 2 moments to prove concentration, whereas some other estimator might require higher moments, median of means has this nice property, we can show this theorem that I just stated before, that we can predict any m observables with bounded norm, bounded by b, to epsilon error from b log m over epsilon squared measurements. Hence, it's logarithmic in the number of things we wanted to predict. And this 1 over epsilon squared is just a standard shot noise, 1 over epsilon squared scaling that come from even in tossing coins to try to estimate the bias of a coin. One could also ask, is it possible to further improve this result? And in the paper, we also show a matching lower bound that says, in order to predict any observable, m observables with norm bounded by b to epsilon error, we would require b log m over epsilon squared measurements. And it's proven by relating this task to a quantum communication task. And in particular, we will see later that this lower bound only applies to learning using classical machines. If we have quantum machines that try to learn quantum systems, one can evade this lower bound. So together, classical shadow formalism is this simple procedure where we do these randomized measurements on the data acquisition phase to construct a classical representation that can be used to do accurate prediction of many properties. Some more concrete examples are shown here. For example, we can use it to predict entanglement entropy of a small region of the system. We can use this to estimate entanglement witness, to estimate quantum fidelity, to predict 2-point correlation function between any 2 points in the system from logarithmic number of measurements, to estimate Hamiltonian, to estimate energy, or even energy variance, which can be useful for checking if it's an eigenstate, or to estimate any local observables. And with this classical shadow formalism, people have come up with a lot of different ways of using it. And here is just a few examples, but now the community has really grown very large, and there are a lot of very exciting applications of using classical shadow in different creative ways. But some of the first few are shown here. For example, because one can use classical shadow to efficiently estimate quantum fidelity and to verify entanglement, it enables efficient benchmarking of quantum systems. For example, here on the left, we compare classical shadow with neural network quantum state tomography by focusing on estimating the fidelity of a noisy GHZ state. So we prepare some state in the lab, but there are some noise, and our goal is to be able to estimate what is the fidelity of the state that we have prepared. And the x-axis corresponds to the probability of error. The y-axis corresponds to the fidelity that's estimated. We see that as the error increases, the correct behavior should go down. Classical shadow with the provable guarantee tracks the true fidelity accurately. However, what we found here is that when we applied neural network quantum state tomography, it was hallucinating a bit, and they thought there was some pattern, and they thought the physical system was actually accurately representing GHZ state, but in fact it's not. So it significantly over-report the true fidelity. So even when the fidelity was around 0.25, the neural network thought that the fidelity was as good as like 0.9. I would say in a lot of cases, neural network quantum state tomography can reproduce or can produce a correct answer, but there are various cases where there's points of failure that it just fails completely, and a priori it's not clear when it will fail. And that's one of the downside of using heuristic methods. Here's a comparison with another protocol by Bridges et al. And we found that using classical shadow, one can estimate entanglement entropy to a much smaller error compared to another randomized measurement-based protocol. So classical shadow has also been used a lot in quantum chemistry simulation. So in a lot of quantum simulation algorithms, one needs to estimate many properties again and again. This appears in variational quantum algorithm, but also in a lot of new algorithms where one try to use quantum enhancement along with a popular classical ground state finding algorithms such as quantum Monte Carlo based algorithms. For example, in this paper published in Nature by Huang et al., they considered this setting where they have a bunch of Walker states trying to do quantum Monte Carlo calculation for finding ground states. And they wanted to use their quantum computer, the quantum computer at Google, in order to help with that. And the way they would design this protocol was that they will, essentially on the quantum computer, they would prepare some state that help with the walking of these Walker states. And in the way that it would help is that one needs to essentially extract a large number of properties from the quantum computer and use those to guide these Walker states. And in order to do that very efficiently, they essentially run the shadow tomography, a classical shadow tomography protocol, towards the end of the calculation on the quantum computer. But more broadly speaking, classical shadow is just a universal way for turning quantum information to classical information, or turning quantum system to classical, which enables a variety of classical computational techniques, such as machine learning, for addressing quantum problems. And as I will talk about later, we can utilize classical shadow to predict quantum phases of matter. We can also utilize classical shadows to train a classical ML algorithm to predict ground state itself. So now I would like to move on to these aspects. The motivating question here is the following. Now that classical machines can efficiently see quantum systems, can we now use them to learn to solve challenging problems in quantum physics? Particularly, we are curious about the question of whether classical ML algorithms can lead to better solutions than any non-machine learning based algorithms. And this was studied in this paper, Provably Efficient ML for Quantum Many-Body Problems, published in Science in 2022. The test is as follows. We have some vector x that describes an n-qubit Hamiltonian. And the goal of the classical machine is to predict a classical representation, such as the classical shadow representation, of the ground state of the Hamiltonian h of x. And this vector x different entries of it could be used to specify the laser intensity, the few body interactions, the magnetic fields, etc. So it's well known that ground state problem is extremely hard. Even when we place a lot of restrictions to the problem, such as focusing only on 2D systems, like a 2D lattice, with the promise of having ground state and the first excited state have an energy level that's gapped by at least 1. And the goal of the machine is just to predict some one body observable in the ground state. And furthermore, we only care about the average case, not the worst case. One can still show that under the assumption that NP-complete problems cannot be solved in randomized polynomial time, no randomized algorithm, classical algorithms, can achieve an average prediction of less than or equal to 1/4 within polynomial time, hence showing that this is a computationally hard problem. So one could ask, now that this problem is so hard, can classical ML algorithms do something useful for this very challenging problem? So note that in order for classical ML algorithm to work, we have to feed it with training data. And here we consider a kind of a standard training data model, which is we have different parameters corresponding to different physical Hamiltonians that have been synthesized in the lab. And now we also have the corresponding output, which are the classical representation of the ground state. And here perhaps we consider the classical shadow representation as the classical representation. So we feed in this whole set of training data, like different parameters corresponding to different ground state, into the classical ML algorithm. And the goal is that after learning from this training data, given a new parameter that's not in the training data and correspond to a new physical system, we want the classical ML algorithm to be able to predict the ground state of that Hamiltonian. So recall that we have this proposition which says that predicting ground state is hard for classical algorithm. In our paper, as well as a follow-up work done by an undergrad at Caltech, Laura Lewis, we were able to show the following theorem, which is we show that a classical ML algorithm can achieve an average prediction error of less than or equal to epsilon using only logarithmic amount of training data and almost a linear computational time. In particular, this classical ML algorithm, they not only just work for a 2-dimensional lattice, it also works for any constant dimensional system, such as a 3-dimensional material. It works for any constant spectral gap. It works for any local observable, not just one body. And it can achieve an average prediction error of any small constant. The scaling with epsilon is quasi-polynomial in 1 over epsilon. So it can go down to pretty small epsilon, whereas the classical algorithm will be saturated, cannot kind of go below this 1 over 4 threshold without solving very hard problems. So the way that the classical ML algorithm works is essentially can be thought of as follows. You can think of it as, like, for example, it's a neural network. And when a neural network is big enough, it has this neural tangent kernel behavior, which means that the behavior of the ML algorithm is the following. Suppose in a training set, we have x1, x2, x3, x4 as the thing that we know. So we have the corresponding classical representation for the ground state of these points. And now we are given a new point x that's not equal to all of them. Now the classical ML algorithm will essentially try to combine and extract from the classical shadow representation for the Hamiltonians in the training set in order to create the classical representation for this new point x. And now from there, one can essentially establish this theorem and establish this comparison between classical algorithm and classical ML algorithm trained with data. And together, what this showed is that a polynomial time classical ML algorithm trained with data can predict much better than any polynomial time classical algorithm. Hence, establishing rigorously that ML algorithm has an advantage over non-ML algorithms. But one would ask, like, why ML can be more useful than ML algorithms? For people that are not so familiar with the inner working and the definitions of Turing machines and algorithms, one would have thought that, wait, ML algorithm, isn't it just a kind of algorithms? A kind of normal algorithms, and hence how can it be more useful? And the answer to this is because if one look very closely, or kind of as what was shown earlier an ML algorithm taking this training set, which is not available for a normal algorithm because they don't learn. So an ML algorithm, it takes in this training set and it can utilize this training set. When it tries to make predictions, all it has to do is to try to extrapolate from the data, try to generalize from the data, and it can be much easier than computing everything from scratch, which for normal classical algorithms, that's what they have to do. And in a previous work, Power of Data in Quantum Machine Learning, we established this complexity theoretic diagram, essentially showing that data can indeed contain computational power that can boost the power of any machines that learn from it. For example, if nature is operating quantum mechanically, and hence when we do these quantum experiments to extract ground state properties to form the training set, now when we have an algorithm that learns from the training set, it can be much more powerful. Particularly in this paper, Power of Data, we established this diagram that says this circle is the problem that can be solved by classical algorithm. This one is the problem that can be solved by quantum algorithm. And the problems that can be solved by classical ML algorithm trained with data is this blue one. Particularly if one can obtain training data that is beyond the possibility or beyond the capability of quantum computation, then it can solve problems that even quantum computers cannot solve after learning from the data. However, if all we can get, if we assume that nature only has quantum computational power, it doesn't have power beyond quantum computation, then this blue circle will be inside the pink one. And one can also conduct numerical experiments. For example, here we look at 2D random Heisenberg model, comparing with a very expensive DMRG calculation from the ML predictions. The ML algorithm just runs in linear time, whereas the DMRG calculations runs exponential in the square root of the system size. But when we just compare the predictions from the exact values from DMRG, we see that they're almost indistinguishable. Here we're predicting the 2-point correlation function in a ground state of a new Hamiltonian. And that concludes the first part. And let me now dive into the second part. So in the first part, we've seen that classical machines, using classical shadow formalism, can see a lot of things about quantum systems. And furthermore, by learning from data, classical machines can achieve capabilities that is beyond any algorithms that do not have learning capability. So as a result, we have seen that classical machines are actually quite good in learning in the quantum universe. One can ask, what about learning with quantum machines? Since quantum machines may be better matched with a quantum universe, can quantum machines learn faster or predict more accurately than classical machines? To formally talk about this, we need to essentially present a mathematical formalism that separates or defines what is classical machines and what are quantum machines. And this is essentially done by these three works: Information Theoretic Bounds on Quantum Advantage in Machine Learning, published in PRL, kind of sets the stage for everything that comes after it. We had this paper, Exponential Separations, published in Fox, which finally lead to an experimental demonstration on the Google Sycamore processor, Quantum Advantage in Learning from Experiments, published in Science. So first, we need to say what are these classical machines and quantum machines. But here we are going to use a more abstract language and call them classical learning agents and quantum learning agents. So classical learning agents, one can imagine them to be a classical ML algorithm, a classical computer, or even just an experimentalist doing experiments. These classical learning agents can receive classical information by doing measurements, by doing experiments. It can process these classical information using classical computer and store classical information in a classical memory. And through these processing capability, receive, process, and store, it will try to make its best prediction about the unknown aspects that it's trying to learn. On the other hand, as quantum technologies start to advance and more components are being developed, such as quantum sensors, long-lived quantum memory using error correction, to quantum computation, we can start imagining in the future, if an experimentalist is equipped with these capabilities, or if we have a very powerful quantum AI model, how can it learn about our world? So in general, what it can do is it can receive, process, and store quantum information. It can receive quantum information by transducing using quantum sensors. It can process these quantum information using quantum computation and store these quantum information in a long-lived quantum memory. And together, using these three capabilities of receiving, processing, and storing quantum information, a quantum learning agent tries to make prediction about the world. And a key question that we're interested in is the following. What are the advantages of a quantum learning agent over a classical learning agent? So while this is a very important problem for understanding quantum machine learning and understanding quantum learning theory, I would also say that this question is important from an even broader perspective. Because essentially this question is asking, in the future, can quantum technology fundamentally alter our ability to learn and to understand the physical world? So while this is a very broad goal, we have to start from somewhere. And in this series of work, what we establish is a collection of exponential quantum advantages for learning different properties of physical systems. For example, this first one is in predicting many incompatible observables. In order to predict all Pauli observables, there's 4 to the n of them, and note that their Frobenius storm is 2 to the n, and hence classical shadow cannot really deal with them very accurately. And more generally, what one can prove is that any classical learning agent, including classical shadow, will require an exponential number of experiments in order to predict all 4 to the n Pauli observables. On the other hand, a quantum agent only requires a linear number of experiments to predict all of these 4 to the n Pauli observables. And deep down, the reason is because they're highly incompatible with one another, and hence there's a strong form of uncertainty principle that limits the capability of classical agent. On the other hand, a quantum agent, by utilizing quantum sensor, quantum computation, and quantum memory, is able to essentially circumvent uncertainty principle and simultaneously learn a large amount of information about these collection of highly incompatible observables. But not only that, one can also prove that there's exponential quantum advantage in performing quantum PCA. Particularly if we have a quantum state, we wanted to estimate property of its principal component, which is just the eigenvector that corresponds to the largest eigenvalue. One can show that classical agent will require exponential time, but a quantum agent only needs polynomial time. The same also holds for uncovering symmetry in dynamics. If we wanted to classify if a dynamic, an unknown physical dynamics, has time reversal symmetry or not, one can also establish an exponential quantum advantage between classical learning agent and quantum learning agents. And finally, if we wanted to learn an approximate model of a polynomial time quantum process, one can also prove that a classical agent requires exponential number of experiments, but a quantum agent only requires polynomial number of experiments. And all of this was established using a new set of learning theoretic tools that was developed in these 3 papers. Particularly, we propose this learning tree representation, which is a model for understanding how classical learning agents conduct experiments, records data, and changes its classical memory state. Each of the nodes on the tree correspond to one possible state of the classical agent, and as it continues to do experiments, and depending on the experimental outcome, it will process or it will walk on this tree. It's essentially a decision tree or a learning tree. So now one can look at how these advantages work on actual experimental devices. So here we're looking at an experiment for learning about incompatible properties, for learning highly incompatible Pauli observables, utilizing a total of 40 qubits on the Sycamore quantum processor, the processor that on Google for developing Google Quantum AI. So to the right, what we're showing here is when we varies the system size and how many experiments are required to predict the properties with certain amount of accuracy. Here, we set it to be not very high accuracy because we were seeing that even with 70% accuracy, the classical agent is already faltering quite badly. So the number of experiments grows too big. But here, these crosses are the best known classical learning approach for learning these incompatible observables. And we see that as system size grows, the number of experiments quickly blows up, which quite matches the rigorous lower bound that one could achieve. So this dashed line corresponds to a lower bound that one can prove using pencil and papers that no classical learning agent can go below this. However, the best known algorithm we found so far is this crosses. We can then compare it with the performance for quantum learning agent. We see that as the system size starts to grow, the number of experiments would only grow linearly, and hence from a logarithmic scale, it looks like a log plot. And while in the small systems, it doesn't outperform the rigorous lower bound, as we increases the system size, we see that the number of experiments at the largest scale was many orders of magnitude better than the rigorous lower bound. And note that if one just kind of extrapolate from these crosses, it would go even further up here. Like maybe it required 10 to the 8, 10 to the 9 number of experiments, whereas the quantum agent only requires less than 100 experiments. So that showcases the advantage in learning quantum states. And I should also add that there's a very nice result from the IBM team that considers these advantages in learning noise, in learning Pauli channels in quantum devices. And they also were able to demonstrate these type of exponential advantages in learning noise on quantum processor when we have a small quantum learning agent that sits on the side. Here's another example that was demonstrated in our paper, which is the quantum advantage in learning unknown physical dynamics. So here, the setting that we consider is that we either have a quantum agent or a classical agent. What it would do is we will give them tons of different physical dynamics. And the goal of the learning agent is to uncover if there's a certain pattern in these random dynamics. And in this case, what we did was we just give them a bunch of different dynamics. Half of them are just general dynamics, and the other half are dynamics that satisfy time reversal symmetry. And our goal is for the quantum agent and the classical agent to figure out what is this hidden property inside the problem. So essentially, we're using an unsupervised machine learning model on the quantum agent and the classical agent. And here's a result shown on B and C. For 1D dynamics, for learning 1D dynamics that we shaped through like this, or learning 2D dynamics that was shaped like this. What we found is that, similar to our proof, the classical agent, using the same number of experiments, is unable to figure out the pattern between the two. So it would thought that the two are just all the same for both 1D and 2D. Whereas the quantum agent is able to accurately see that, oh, there's the general dynamics, it can group them together, and there's the time reversal symmetric dynamics, and it can group them together, forming two clusters, essentially identifying and uncovering this hidden symmetry for the collection of physical dynamics that we just give them. And that showcases that for learning about physical systems, for learning in the quantum universe, quantum machines can learn much faster and predict much more accurately than classical machines. Together, these results establishes these separation between three families. We have classical machines that cannot learn. They're just normal classical algorithms, the standard one. And we have found that, say, for example, in predicting ground states, classical learning algorithms, classical learning machines can be much more powerful than classical machines. And then in the second half of the talk, we also looked at how good quantum learning machines can perform. And we found that in many tasks, including uncovering hidden symmetry in dynamics, quantum learning agents are much more powerful than classical learning agents. And hence, establishing these three-level hierarchy from classical machines, the weakest, to classical learning machines in the middle, and then the quantum learning machines being the strongest. So to conclude, there have been significant recent progress in understanding how we can learn in the quantum universe. However, I would say so far, a lot of it still focuses on lower level tasks, like predicting properties, classifying phases, etc. And going forward, I think with all the tools that we have developed, we can start to see if we can create rigorous ML algorithms for higher level tasks. For example, some of our recent results shows that one can design provably efficient algorithm for designing quantum circuits. And can we also extend that to designing quantum protocols or even designing quantum algorithms, like uncovering new algorithms with quantum advantages that we don't know about before? And if we're even more ambitious, can we create rigorous algorithms that can discover new physical phenomena happening in this world? So before concluding, before ending, I wanted to just say, what are some of the long-term ambitions of this research program for learning in the quantum universe? I would say there are essentially two, which we try to develop over time. And a lot of these results that I talked about were motivated by these two long-term ambitions. The first one is we would like to further develop our understanding of learning to accelerate and automate the development of quantum science or even science in general. And perhaps one day, if we have developed our understanding enough, maybe it would give rise to an algorithmic theory of science. What it means by that is we can just write down a rigorous algorithm, and by just running that algorithm, one would be able to discover everything yet to be discovered in science. The second very long-term ambitions is that we're hoping that by having this understanding of learning and of discovery, of scientific discovery, we will in the future be able to build a powerful quantum machine that is capable of learning and discovering new facets of our universe beyond the combination of humans and classical machines. And that's it for my talk. Thank you so much for listening.
Just a minute, okay? Thank you, Robert. Very nice talk. And also very futurist.
Yes.
Yeah. Okay, so now I have time for questions. Is it possible if you come here? Você pode vir aqui, eu posso no microfone. Acho que você sentar aqui, sei lá. Pode ficar um pouco mais próximo da câmera. Aí vai, ok. Tá bom.
Okay. Thanks for the talk. It was very nice to see all these results. I think it was very optimistic. I have a question. You said about the quantum agent. So
Yes.
I think he has to keep the memory, the knowledge he acquires along the process. And at some science in the amplitude of the states of this agent, independent of the quantum system we are using to create this quantum agent, right?
Yes.
But if you want to use this information in our experiments or to learn something, we have at some moment make measurements, right? To get information from the quantum agent to the classical realm where we live. How this is done, and this information acquirement is also done in polynomial time, because you have to do in the end tomography, for example, of the quantum agent. I think everything everything is not very useful. I think it's not the case, but just to know, how do you get this information back?
Yeah, that's a great question. So indeed, because ultimately we want both the classical agent and quantum agent to report back to us, which we are a classical agent, and hence there must be some form of measurements and collapse that would happen. So for example, for classical agent, measurement already happened at the very beginning. Like every time you do experiments, they will collapse quantum things, and then you just process everything classically. On the other hand, in quantum agent, what happens is that we can first show it out, like the quantum agent just do its own thing. We don't talk to them. Quantum agent go do experiments, go to use quantum sensor, store it in quantum memory, keep a quantum state of its memory. So the quantum agent also maintain its own quantum memory, but that's in a quantum state. It do this processing, and at the very end, the quantum agent needs to report the answer to us. So for example, we can start asking questions to the quantum agent. So after it learns, we just ask questions to quantum agent, like, could you please make a prediction for this scenario? Could you please make a prediction for that scenario? And the quantum agent just reports it back in a classical way, like just essentially one can also think of it as we're just measuring a bit of the quantum agent, and then that bit is the answer for quantum agent. So yes, so the measurement still happens, but in a way one could think about it as we're not gonna do a tomography of quantum agent. The quantum agent can be extraordinarily complicated. It can maintain some crazy quantum state. We're not going to do a tomography. We're just going to interact with quantum agent just like how we interact with like ChatGPT. We just ask it questions and it will provide answer. And when it's providing answer, there is measurement, there is collapse that would happen. So the quantum agent has to kind of collapse itself to produce a classical answer back to us. But it can also continue to maintain quantum memory. One can imagine that this is just like a big quantum computer that has learned some things and it maintains its quantum state. It tries to protect its quantum state while answering questions to us. Actually, that's also like how a lot of these results work. Like for example, in order to predict many incompatible observables, what happens is the quantum agent will do its experiments, order n experiments. After doing it, it will keep its model. It would generate its own model on the quantum memory that it's holding. And now we would just ask questions to it, like, please predict this Pauli observable. Please predict that Pauli observable. We can ask it for any number of times. We can ask it for the entirety of Pauli observables. And every time when we ask it, the quantum agent will always provide the correct answer. And that is what I mean here, that it can predict all Pauli observable. So we are not going to do a tomography. That will be very, very expensive. We're just going to do an interaction. We're just going to interact with quantum agent. Another example is this. Like, let's say we ask the quantum agent or the classical agent to try to classify dynamics. Like there are some unknown physical dynamics that's happening in nature. The agent try to do experiments to figure it out. At the very end, the agent just need to report, does it have time reversal symmetry or not? And hence it just produced one bit. The inner working, like the memory state, can be very complicated in the quantum agent, but at the end it just spits out one bit of information back to us, and hence that just requires doing a very simple 1 qubit measurement. So I hope that answers the question.
Thank you.
Okay, we have time for more questions. Okay, while people in the audience are thinking about the questions, I will do some questions. Can you explain, maybe not using math theorems, in a simple way, why is quantum learning, why is easy for quantum, what is quantum learning easier, than classical learning? Why this quantum advantage? Whether the large Hilbert space or superposition or any properties that you use the attribute to the quantum world, such as entanglement and so on?
Yeah, that's a great question. To be honest, all of these different advantages come from different possible mechanism, come from different mechanism for how advantages could arise. I don't think there's no way to just pinpoint down a single origin of the advantage, because in a way, some of these are just very different. They're very different mechanism that lead to advantage. But roughly speaking, one can look closely at what is the difference between quantum and classical agents. So in relation to the previous question, so in a way, quantum agent, it it can process quantum information for a very long time, and only until the very end, when we ask them question, then it will have to do measurement and collapse and tell us the answer. Whereas for classical agent, every experiment, it will cause collapse. And for example, for the case of predicting many incompatible observables, the situation there is that for classical agent, every measurement, it would just collapse the system. And when it collapses the system, it will essentially, whenever one does a collapse, one does a measurement, there will be uncertainty principle kicking in. So every time we measure it, you will only be able to measure in a certain basis, and hence you will not get information about other bases, etc. So this uncertainty principle strictly limits its ability to learn. And uncertainty principle only arises when you do measurements. On the other hand, the quantum agent, what it could do is it can keep a bunch of things in its quantum memory, and then it can do a more sophisticated quantum information, like quantum data processing procedure. So it can like entangle between multiple copies, and then try to weakly extract information without perturbing multiple copies. So there are certain kinds of enhancement that can only be done when we get multiple copies or multiple samples of a quantum system, and now doing some entangled measurement across them, and now suddenly one can perform some kind of weak measurement that only only extract out the necessary property that we wanted, and then providing that answer while keeping a lot of the state in coherence. So in that sense, quantum agent can surpass uncertainty principle, even though there's also measurement involved. But essentially, it's like when it can manipulate a large amount of quantum information or many copies or many samples of the quantum system that is trying to learn, then suddenly it can evade this uncertainty principle when it's only performed on one sample at a time. Like in classical agent, getting one sample, one would do a measurement, and it would collapse, and then that collapse would cause uncertainty principle type effect. But quantum agent, it can have multiple copies, multiple samples, and then perform some measurement jointly and entangle measurement on all of them that prevents certain collapse behavior and evading uncertainty principle for single sample measurements. So that's one way where this could happen. That corresponds to this disadvantage. But these other ones, they correspond to different mechanism. But in a way, the key difference is really like for classical agent, every time we do experiments, it can only extract classical information. So there's this bottleneck from quantum to classical. Quantum agent, at the very end, when we ask it question and then it provides answer, there's also a bottleneck from quantum to classical. But before that, it can do everything in quantum form, and that gives power. So I would say that's one way how this arises.
Okay, thank you. Okay, we have time for one more question. Okay, you...
Não tem. Não.
Okay, there is one more question here, please. Come from here.
Hello, Sir Huang. Thank you for the talk. Sir, I have a question. I was really astonished by the long-term achievements that you thought that we will have. So sorry for the silly question, but you think they are possible, and when they will be possible? Please, I would really like to know.
Because like the first one, I'm not entirely sure. I feel like science development as a whole might be just impossible to theorize or to have an algorithm for it. I'm also not sure this one I'm not super sure, but in a way, humans are kind of like algorithmic, right? So we act based on certain algorithm, our brain encodes the algorithm, and hence we can do science, and hence machine must also be able to do science. So that I think is possible. And again, also like in Google DeepMind, there are a lot of scientific inquiries and scientific discovery that were made using these ML algorithms, using learning machines. But I guess my goal is even further than that. Not just we can use them heuristically, but to also develop an understanding on how we can accelerate and automate the development of science. So I would say the first step, I mean, it's already in progress. People are, I would say, a lot of the things that I talked about are already like very early version of this first step. The second one, of course, it will also depend on the time scale for how quantum technology is developing. Right now, people are very focused on developing full-Turing quantum computer, which I would also agree that that's a necessary component in order to achieve the second goal. And yeah, and then from there, how can we build a quantum machine that can discover new physical phenomena? I would say there are multiple ways that could came about, but having quantum sensor, having quantum computer, having long-lived quantum memory with error correction, and having a way to combine all of them is still a technological barrier that needs to be overcome. So I'm not entirely sure when that would be. And furthermore, after we have all the quantum technology, it's still not enough. We need to write down a very good quantum machine learning algorithm, which you still don't have, that can really learn and try to discover physics. And that's really another big challenge. So I don't think this is an ambition that can be achieved in the next few years, but something I would say it's much more long-term. But I do believe that variants or versions of these will be achievable. But perhaps it would still require maybe 30 to 50 years until we can really do something like this.
Thank you, Huang.
Okay, so more questions? Okay, just one more question. Sorry for that. Taking third time. This is a general question, not about your talk. But as here in the audience, you have undergrad student, master's student, PhD student, professors. So as we are very young and with very good results, very amazing results, publishing very important journals, can you give some advice how to succeed in career as you are doing?
Yeah, I would say different people have different path to success. At least for me, I think as a theorist, as a theorist that works in an intersection of theoretical physics, theoretical computer science, and applied math, for me, I would say the path that I've been taking on so far was I try to ask some of these very big questions, and kind of vague one and kind of philosophical. And as a starting point, because these questions are too vague, for example, how can classical machines see quantum many-body system? Like that doesn't even mean anything. What I try to often do is try to formalize them. So I start out with some ambitious question. I don't know how to answer them. I don't even know what they actually mean. But then try to formalize them, try to pinpoint down, try to set up a mathematical model that seemed to reflect that question the best, and then slowly go from there. So I try to formalize it, see if it makes sense, and see if one can now answer that question in a mathematical set way. If not, try to even pinpoint down further. For example, it was kind of how I also structure this talk. Like we start out by asking, can classical ML solve some hard problems, and can they yield better solutions? But that's still very vague. We need to pinpoint down to certain problems. So then we started focusing on predicting ground states, and from there try to go even further down. Is predicting ground state actually hard? Can we prove that it's hard? Can we utilize the existing tool to prove that it's hard? Okay, now we prove proposition one. How can we do something useful using classical ML algorithms? And then try to better understand, clarify, what does it mean to have a classical ML algorithm as formal as possible? So at least that's kind of often the way, the path that I took which I would say I know a lot of different scientists. They took different paths. Some scientists, they're much more numerical minded, so their goal is to look at some puzzling physical dynamics and try to use numerical tools in order to simulate it in a very heuristic or numerical fashion, try to understand it using numerical tools, etc. But me as a theorist, I like to go down this route of just like asking big questions, trying to formalize them, and trying to answer them. And I try to be I try to not set any limit. So I think sometimes people would feel like, oh, I'm a theoretical physicist, and now it seems like in order to answer this question that I really like, I really need to use a lot of theoretical computer science tools or even learning theory tools. What I just do is I just go and learn all of them if I find them to be useful for answering the bigger question I want. So I usually take this approach, and so far it has been, I think it has been a successful path towards it. And yeah, and there is a lot of learning that have to happen, and also like a lot of the questions that I ask, which I'm interested in, I don't know where it would lead to. For example, initially I have no idea about different properties that was used in proving, for example, this theorem. We use a lot of tools from quantum many-body physics, like spectral flow, and also a lot of tools from machine learning. I don't know them a priori, but because I wanted to answer this question, I just go and learn them. So I feel like this organic behavior, process of asking a question and try to formalizing it, try to make it answerable. I think that's also a huge step. Like many steps is required. You need to make that question answerable, and that would take time formalizing it. And then after that, try to learn all the possible tools to answer them. So that's the path that I've been taking, and I believe for people that are much more theoretical minded, this is a useful path to take.
Thank you. Very nice advice. Do you have time for one more question? Because in the YouTube, let me see.
Tem um antes.
Okay. I don't know if I got the question properly. The life is quantum. Okay. Is fractal spinning? In fractal spinning? I don't know what that means. Okay, sorry. Did you get?
No, sorry. What was the question?
Sorry. Neither. So, okay. Then sorry for that. Maybe next time. Okay.
Yeah.
Let's thank you, Robert, again for that very nice talk. Okay, Robert. Thank you.
Yeah.
So I
Much.
hope to see in the near future and maybe a next conference next year. Okay.